Thank you, Claire, and good morning, everyone, and welcome to this training session. As you can see from the bottom left-hand corner of your main screen at the moment, my name is Cliff Curtis. Just let me give you a little bit of background about my relevant experience to be able to do this training event this morning. I was a teacher, former teacher of chemistry to both GCSE and A level, and also Oxford and Cambridge entrance exams when they were available, but stopped back in the 1980s. I taught for 38 years in UK secondary schools from 1973 through to 2011, so I retired 14 years ago. Also extensive experience as an examiner. I started examining in 1984 and finished in the end of 2017 for 8 years, from 2010 through to the end of 2017. I was actually the principal examiner for this particular qualification. The last papers that I wrote that were sat by candidates were the 2019 papers for summer. I've also been a trainer for Pearson from 2010 right up to date, of course. I've done both online and face-to-face training overseas. And also, if you are familiar with international A-level chemistry, you may have seen my name as co-author on the 2 student books that are published by Pearson's to support the international A-level chemistry specification. Okay, so that's enough about myself. Let's get on to what today's training is all about. There we go. Okay, on to the second slide. This particular training is designed for teachers teaching who are looking to teach the Pearson Edexcel GCSE chemistry specification. And the object of the aim of this particular session is to understand how the qualification is actually devised and to have a look at the content that's in the qualification, to try to understand the assessment of the qualification, to explore how to plan the course and or lessons, to understand the question types that you're going to be faced with if your candidates are going to be faced with, to understand the assessment objectives for the qualification. If you're not aware of what the assessment objectives are at the moment, or have never heard that particular term, then don't worry, because I will explain everything with regard to assessment objectives and what they're all about and why they're necessary and why they're very useful for both the writers of the exam papers and also for both you and your students. And then to give you an opportunity to practice using the mark schemes using exemplar student work. So I've got some student work that I'm going to ask you to look at and try and mark. And then you can compare your marking against my marking to get an idea of how the examiners go about marking your students' work. And then last but not least, to identify all the support that's available from Pearson's. So that's the agenda. A brief introduction to Pearson for those of you who are not that familiar with Pearson. Then to have a look at the assessment model, to look at the assessment of this particular qualification. How do we actually go about assessing your candidates and giving them their grades? Some ideas on planning the course, which are my ideas, not necessarily Pearson's ideas, but something for you to perhaps consider. Looking at the various question types that are on the papers, then a detailed look at assessment objectives, and I've tried to convince you that they are very, very important for you to get a really good understanding of. and then to give you an opportunity to look at some student work in AO2 and AO3 and mark it using the official mark schemes, and then finally looking at the support. So first of all, welcome to Pearson. You will have in your pack a PDF version of the PowerPoints, or of all of the slides, so you'll be able to read all of this at your leisure. But as you can see, we're the world's leading learning company. And as the UK's largest awarding organisation, we think we are best placed to provide qualifications aligned to the British system. Okay, and we stretch back over 150 years, and we partner schools, universities, employers worldwide. 3 million students a year pass through our hands. So you can see we're quite an extensive organisation. So let's get down to the important factors with regard to this particular qualification. The assessment model, first of all. The key features are there are actually two choices of assessment models that we've got, both linear and modular. This particular presentation is focusing on the linear route. There is a separate presentation dealing with the modular route. So if you are interested in the modular examinations as well, then I suggest you sign up for that one and have a listen to the presentation on that. Okay. There's no separate practical exam because practical skills are assessed on the papers. So no separate practical exam needs to be taken at all. The papers in both the linear and the module have similar question styles. And as I said, we'll be looking at the question styles a little bit later. And there's no tiering of the papers. There are two papers in the linear section, and both of them are graded from 9 to 1. So let's have a look. As I said, this particular presentation is focusing on the linear route assessment. There are two papers, and we'll have a look at the content of both papers in a moment, and they have got to be taken together in one examination series. So either in the summer or the autumn series. The grades are calculated on the raw marks that they achieve, so there's no uniform mark scheme like there is in modular assessment. So we simply use the raw marks that they get to calculate their grades. The students can resit the assessments, but they have to sit both papers together in one exam series. So let's say, for example, they took the exams this summer in 2025, and they wanted to resit because they felt that their exam grade was not up to the ability that they can actually achieve, then they could resit at a later exam series, but they would have to sit both papers. They can't just sit one and try and get a better mark in one and combine it with the other one from the previous series. They've got to sit both papers in one exam series. So that's very much different from the modular system. The grade the students receive are calculated at the end of the exam series in which they sat their assessments. What about specification content? Well, I was particularly heavily involved in the specification content. Myself and the co-author of the International A-Level student books, Jason Murgatroyd, he and I sat down and we wrote this particular specification. And we split it up into 4 major sections: principles of chemistry, inorganic chemistry, physical chemistry, and organic chemistry. And you will see the typical sorts of things that are in the GCSE specification contained within each area. So principles of chemistry, you would expect states of matter, elements, compounds, mixtures, atomic structure, periodic table, chemical formulae, etc. And all 3 types of bonding that you'd expect at GCSE level: ionic, covalent, metallic bonding is covered, and there is some work on electrolysis. In the inorganic section, we decided to focus mainly on group 1, group 7, and there's some work on gases in the atmosphere, reactivity series, extraction and uses of metals, acids, alkalis, titrations, acids and bases in salt preparations, and the usual chemical tests for both ions in solution and in solids, and also for gases. In the physical chemistry, three major sections: energetics, rates of reaction, and reversible reactions and equilibria. And the organic chemistry section from the previous qualification has been increased quite significantly. There's quite a bit more work. After we've done introduction and crude oil alkanes and alkenes, we've introduced quite a bit of work on alcohols, carboxylic acids, esters, and synthetic polymers. This was in response to the feedback that I was getting in the face-to-face meetings that I was having with teachers overseas, who said that the previous qualification didn't have enough organic chemistry in it to prepare students for A-level. So that's why we've introduced quite a bit more organic chemistry into this particular specification. So I mentioned before, there are two papers. The first paper is a 2-hour written exam. It's got a total number of marks of 110, and it's just over 60% of the total score for the international GCSE. And if you've had the opportunity to look at your specification, you will have noticed that some of the statements in the specification are in bold type and have a C, capital C prefix. This particular paper does not test those topics that are in bold and have a C prefix. However, the questions could be set from any of the four major areas of principles of chemistry, inorganic chemistry, physical chemistry, and organic chemistry. So you have to be aware that the students need to revise all of the material that's not in bold for that particular paper. But the second paper, that's a 1 hour, 15-minute written examination, the total number of marks is 70, which comes out to around about 39% of the total international GCSE. And this assesses all of the content, including the content that is in bold and has a C prefix. Now, one of the problems that we have faced in the past, when we received some comments from teachers saying, but you were assessing in paper 2 information that was not in bold. It does say very clearly in the specification that all of the content can be assessed in this particular paper. So both you and your students need to be aware that they need to revise everything that's in the specification for this particular paper. And once again, it can come from any areas, any of the four topic areas. Some of the bold statements cover some of the topics in greater depth. So if you look down through the specification, you'll see in some of the areas that there's a certain amount of material that's not in bold, and then there's some extra specification items that are in bold that go into greater depth in that particular topic. Some of the C prefix bold type is just simply a section on its own. Like, for example, reversible reactions and equilibria is totally bold type. Okay, let's have a look. I'm just having a look to see if that somehow can't bring up the chat box. So just let me click on OK. I just want to see if there's anything in the chat box at the moment. It doesn't look like there is. Okay, right. So let's have a look at the assessment of the qualification. The first thing you notice, if you've got access to the specification or you've had a close look at the specification, you'll notice that each topic and subtopic contains several statements. For example, there's the very first set of statements on states of matter, and they have got little numbers next to them, 1.1, 1.2, 1.3, 1.4, and you'll see that the 1.1 to 1.4 are not in bold type, so they can, those statements can be assessed on both paper 1 and paper 2. Sorry, just on paper 1 only. But 1.5 C, 1.6C and 1.7C are in bold type. This is where we've got some gone into further depth on this particular topic, and those can only be assessed on paper 2. So 1.1 all the way through to 1.7 can be assessed on paper 2, but 1.1 to 1.4 can be only 1.1 to 1.4 can be assessed on paper 1. So I hope that's nice and clear. All right, well, if you've got access to your specification, then have a look at the specification at the moment, and if you can bring it up from on your screen from the download if you want to, and try and work out which specification statement the following questions assessing. Clue is topic 2 inorganic chemistry. Say you go through the whole of the specification, just look at topic 2 inorganic chemistry. There's no need to put your answers into chat. There's quite a number of us here, so it will just fill up the chat box. I suggest you might make a note of the answer, because you might want to start using this activity with your students. You're very welcome to do so. Okay, the material in the PDF version is yours to use as you see fit. Right, if you've managed to find it, it is in fact gone again. I don't understand why this is happening. Sorry, there we go. It is 216. Understand how metals can be arranged in the reactivity series based on their displacement reactions between metals and aqueous solutions of metal salts. Now, the reason why I got you to have a look at this is to get you to appreciate that every single question or part question that is set is designed to test a particular specification statement. You will appreciate, of course, that even across the papers 1 and papers 2 taken together, it's impossible to include every single specification statement. And the way in which the papers are constructed is that the chief examiner decides which particular specification statements that he wants questions written on for the papers for both paper 1 and paper 2, and the paper writers then go away and construct questions to access those particular statements. And obviously, some statements will be assessed in one session and then possibly in another session, but two sessions following one another will not be assessing identical specification statements. So the chief examiner will be looking at what's in the previous papers and saying, right, well, look, we assessed those specification statements. This time, let's assess these specification statements in this particular series. So that way, of course, both neither you nor your students know exactly what's going to be assessed, but you do know that it's going to be from the statements that are in the specification. Okay, there's another one, activity 2. Have a look at that one. Explain why the new equilibrium mixture contains less NO2 than the original equilibrium mixture. And the clue to finding where this one is, it's in topic 3, physical chemistry. And you have a look and I'll bring up the answers on the next slide. So the first question is explain what is meant by the term dynamic equilibrium. And the second one is you've got some NO2 and NO4 put in a sealed gas syringe. Explain why the new equilibrium mixture contains less NO2 than the original equilibrium mixture. As I said, it's topic 3, physical chemistry. Okay, hopefully you've had a chance to pick this out, and you'll realize, of course, that this is coming from the reversible reactions and chemical equilibrium section. The first one, explain what is meant by dynamic equilibrium, is 3.20c. Know that the characteristics of a reaction at equilibrium are the forward and reverse reactions occur at the same rate, and the concentrations of reactants and products remain constant. That's all that the students need to write down in answer to that question, and they can write those two statements down word for word from the specification. And I would very much encourage the students to try to learn those statements off by heart so they can just repeat them, because that is what the examiners will be looking for. Whenever it's something that the students are expected to know, then you'll see that the mark scheme reflects exactly what is written in the specification, and the students are quite at liberty to write down what's in the specification word for those particular types of questions. They don't have to put these things in their own words, and they certainly don't have to add anything extra to it. So it's just those two statements. Now, the next bit is to explain why there was more NO2 in the final mixture, and this is 3.22c. Know the effect of change in either temperature or pressure on the position of equilibrium in a reversible reaction. And this particular one was an increase or decrease in pressure shifts the position of equilibrium in the direction that produces the fewer or more moles of gas. So the increase goes in the direction produces fewer, and the decrease goes in the direction produces more moles of gas. Now, one thing that you will notice in this particular specification is there is no mention whatsoever of Le Chatelier's principle. Now, it doesn't mean that you don't have to teach Le Chatelier's principle. That's entirely up to you. But you have to be aware, and I'm going to mention this more than once during the course of this presentation, because it is something that is very dear to my heart, that any use of Le Chatelier's principle will be totally and utterly ignored. So if they decide to make use of it and write comments relating to it, then it'll be ignored, so the students will be wasting their time. So quite a useful piece of information, I hope, for you. And I will come back to this later, because I'm a great believer that Le Chatelier's principle causes more problems than it actually solves. Well, I'm not sure it solves any problems, to be quite honest, but that's my own personal opinion. Okay. Because, of course, I've spent many, many years marking examination papers and 8 years being the principal examiner, I've built up quite an exhaustive knowledge of some of the common errors that are seen in answers. And I've just selected a few of them today. There's some of the more common ones. One of them, referring to intermolecular forces of attraction when discussing the properties of substances with giant covalent structures and ionic compounds in metals. Giant covalent structures are not molecular compounds, despite what some textbooks decide to state, and despite the fact that the generosity of the examiners do allow things like macromolecular to creep in, I would very much suggest that you don't describe giant covalent structures as being macromolecular. There are a lot of very good reasons for that, and I might come on to it a little bit later. Ionic compounds, of course, are again not molecular. They're an amalgamation of ions all joined together in a giant lattice. And again, metals. The common view of metallic structure at both GCSE and A level in the two Pearson specifications is that of cations surrounded by delocalized electrons. I'm not very convinced that that is the correct description, but that's the one that is used in both the international GCSE specification and international A-level specification. Again, not molecular, but you'll be surprised at how many students refer to intermolecular forces of attraction when they're trying to explain the properties, like why do giant covalent structures have high melting points? And they talk about strong intermolecular forces of attraction. This, I think, comes because of this term macromolecular. And they think, oh, if they're very large molecules, they must have strong intermolecular forces of attraction. They're not molecular, so they can't have intermolecular forces of attraction. They've just got strong covalent bonds between all the atoms. Okay, anyway, right. So next one. You'd be amazed at how many students state that the reason why simple molecular substances have low melting points and boiling points because the covalent bonds are weak and therefore they require little energy to break. So instead of talking about the fact that the intermolecular forces of attraction are weak and therefore you need little energy to overcome them. Losing marks when writing chemical equations. Gosh, I wish I had a pound coin for every time that I've seen H for H2 or MgCl for magnesium chloride or NaCl2 for sodium chloride. Number of times I have seen the equation for the reaction between sodium and chlorine being Na plus Cl2 arrow NaCl2 is unbelievable. So one of the things that, and this happens at A level as well, believe it or not, and one of the things that I always used to do with my A level students is I always got them, when I first got them into the first year of their A level course, I would actually give them as a homework assignment a whole series of compounds and ask them to write the formula for them before I actually got started on teaching the A-level course, to try and remind them of what the correct formulae are for these compounds, because if they get them wrong in an equation, they lose all the marks in the equation. They've had it. They've got no chance at all. Another common error is referring to changes in energy, usually kinetic energy, of the particles when explaining the effective surface area of a solid or concentration of solution on rate of the reaction. It's very common for students to want to put down in their answer everything they know. And so they'll start off by writing some good chemistry, saying the reason why the reaction increases in rate with an increase in concentration is because there are more particles in a given volume and therefore there are more successful collisions per second, and also because the particles have more energy and therefore the activation energy, more particles exceed the activation energy. Now, if they add that to their good chemistry they've already written, they have to be penalized because they're writing some chemistry that's incorrect. So that's something to be aware of as well. Another one, providing contradicting information when explaining the effects of change of a variable on the position of equilibrium of a reversible reaction. So, for example, for that particular reaction, which you can see is exothermic in the forward direction, you will find that students may well say a decrease in temperature will increase the yield of ammonia, which of course is correct. And then they will go on to say, as the equilibrium shifts in the endothermic direction, thinking that delta H minus is endothermic. Well, it's not, it's exothermic. So they have written down something that's incorrect and therefore obviously have to be penalized. Once again, do apologize, but I'm not going to apologize. It's so important that me to mention, Luscitelli's principle is not on the specification, so they shouldn't be making any reference to that. Mark schemes do not give credit to an idea that a reaction wants to resist a change or moves to oppose a change. There's no marks whatsoever for writing down this sort of information. Okay, activity 3. Now, you might like to just jot these down on a piece of paper. Again, please don't put anything in the chat box because there are too many of you here at the moment. This is a question that I wrote. In fact, all the questions we've looked at so far, ones that I wrote quite a number of years ago. SiF4 and SiCl2 have simple molecular structures, but SiO2 has a giant covalent structure. Now, I've picked on this one to emphasize some of the errors that I've mentioned that students often make when answering questions. So explain why the boiling point of SiCl2 is greater than the boiling point of SiF4. And part 2 is explain why the boiling point of SiO2 is very much greater than the boiling point of SiCl4. So what are the essential points to include when answering these two questions? So you might just like to jot down on a piece of paper what you think are the essential points they need to get down. I'm not asking you to construct a perfect answer. Just jot down the 2 essential points that you think for number 1, the 2 essential points for number 2. And I've got a little table on the next slide, not listing the essential points, but outlining the differences between simple molecular and giant covalent substances. I'll give you a moment to come up with your thoughts. Okay, let me share with you what I think are the 2 essential points for each one. The first one, of course, is that SiCl4 has a larger relative molecular mass, and therefore the intermolecular forces of attraction will be greater, and therefore there will be more energy. So I don't think it was essential to write down the business about the larger molecular mass, but you could simply say that SiCl4 has stronger forces between the molecules, and therefore more energy is required to overcome them. And in the second one, you would say that there are very strong covalent bonds between the atoms in SiO2. So the amount of energy required to break those strong covalent bonds is greater than the energy required to overcome the forces of attraction between SiCl4 molecules. So that would the way in which I would go about answering that question. Now, I've just produce a little table for you to emphasize some important things that you might like to share with your students. As I said, you're quite welcome to use any of the slides from the PDF slideshow that I've produced for you, and to emphasize the major differences between simple molecular and giant covalent. And the ideas that the students need to get between their heads are that covalent simple molecular compounds exist as simple molecules. I know the adjective simple molecular tells them that, but they still sometimes just don't get it in their heads. That there are weak forces of attraction between the molecules. The forces are easily overcome, and therefore they tend to have low boiling points, low melting points. The stronger the intermolecular forces lead to higher boiling points. Okay, a giant covariant structures is a giant lattice. It is not molecular. And that's the emphasis that I really would like you to stress to your students, that these substances are not molecular. They have very strong covalent bonds between the atoms, lots of energy needed to break the bonds, hence high boiling point, high melting points. There are no molecules, so no intermolecular forces. Okay, so please feel free to share that slide or an adaptation of it with your students as you see fit. Notice some of the terminology here as well. The better terminology is that forces are overcome, not broken, but bonds are broken, not overcome. Okay, it's not that we as examiners will penalise incorrect use. If they talk about the forces being broken, we won't penalise that. Or if they talk about the bonds being overcome, we won't penalise that either. But the better terminology is the forces overcome, the bonds broken. Okay. Just a quick note about the assessment objectives, because as well as assessing a particular statement from the specification, each question or part question is also linked to a particular assessment objective. And we will be looking at assessment objectives in a lot more detail later in this particular presentation. But there are three of them that are labelled AO1, AO2, and AO3. And you'll notice that there is a certain percentage of marks allocated in each of the papers to AO1, AO2, and AO3. And that's very important because later on I'll be stating the major reason for the assessment objectives being in existence. One of the major reasons is to make the exams fairer year on year. So there are always between those parameters the number of questions set targeting AO1, AO2, and AO3. And we don't deviate outside of those, okay? And again, don't feel you have to take in all this information, but you'll see that there is an equivalent breakdown for AO1, AO2, and AO3 based on 110 marks and 70 marks for papers 1 and 2. So in paper 1, you have to get between 23.2 and 25.7% marks. So it works out at between 23 and 26, obviously in practice, because you can't have a point of a mark. Okay, as I said, we will be coming back to this later. Okay, the next item on the agenda is planning the course. And how do you make sure that you cover all of the content? Well, there are three major things that you need to be aware of. One, of course, is the specification, because all of the statements must be covered during the time available to teach the content, since questions can be set on any one of them in paper 2. And in paper 1, of course, all of the statements that are not in bold must be covered for paper 1. Okay. The second is a scheme of work. And Pearson's have produced a scheme of work, and I'm going to give you an example of it on the next slide. You may use that scheme of work and or adapt it to suit yourself as you see fit, or indeed, of course, you can take the good points out of it and produce your own schemes of work. But I'm sure all of you will produce schemes of work for a particular teaching session. I tended to try to produce mine for the whole of the year before I actually started. And once, of course, I've got it done for a particular year, the next year I teach that particular section of the specification. All I need to do is to make some amendments based on the experience I've had teaching it the previous year, if amendments are absolutely necessary. And the last thing, of course, is you have to then break down your schemes of work into individual lesson plans, and you may have instructions from your senior management team that you have to produce lesson plans. And if you do, of course, The lesson plan is a detailed description of the course instruction for any particular lesson. It's developed as a guide, really, to guide your class learning. The details that's in it will vary depending on the preference that you have, the subject that's being covered, and of course, most importantly, the needs of your students. There may be requirements dictated by your school regarding the plan, so you may have to follow a particular format. But it's a plan at the end of the day that's your guide for running a particular lesson. And it's going to include the goal and what the students are expected to learn and how that will be reached. And I've got a bit more details about the way I used to produce lesson plans in a moment, which you can have a look at and decide whether they suit your particular method of teaching. The specification document is on the Pearson qualification website. And as I said, it covers everything that you need to teach. And it's also got a lot of information about the way in which the qualification is assessed, etc. So I strongly suggest that, well, yeah, it's essential that you download that and have it a copy available. You can, of course, get a hard copy sent to you by Pearson's, but you can also download it and have a hard copy onto your own personal computer. Okay. Again, on the Pearson Qualifications website, on the International GCSE section of it, there are an example scheme of work, and that's the very first two lessons that are contained within it, and you can see it's an incredibly detailed scheme of work, and it goes through the whole of the specification. So again, it might be well worthwhile you downloading that, having that onto your computer, and use it as you see fit. Take out the good bits that you like and add in your own as you see fit. Okay, you don't necessarily have to use all of the columns there in your scheme of work. You may cut it down to just simply specification reference, suggested activities and suggested resources, and leave out the last two columns. But it's useful if you're interested in skills being assessed and acquired. They're down there in those last two columns as well. Okay, so again, these are my ideas and not Pearson's suggestions as to components of a particular lesson plan. These are how I when I was a head of chemistry, asked my departmental members, the teachers in my department, to consider when producing a lesson plan. There are, of course, many formats, but I think most of them contain these sorts of elements, typically in this order. The first one being just simply the title of the lesson. Second, the time required to complete it. Third, the list of required materials. This could be worksheets that you're going to hand out, or indeed, of course, if it's a practical you're doing, then it will be a list of all the equipment and the chemicals that are required. A list of the objectives, i.e. what the student is expected to know by the end of the lesson and what you hope they will know. Whether they do or not, of course, is another matter, but it's useful to write down what you expect them to know. A lead into the lesson that focuses the students on the lesson skills or concepts. This could include showing pictures or models, asking leading questions, or reviewing previous lessons. If you are an experienced teacher, you will be of chemistry. You'll be well aware, of course, that chemistry very much builds on, the knowledge of chemistry builds on what they've done before. And so there's sometimes it's easy for us as teachers to assume that the students have a full working knowledge of what you have previously taught them. And that may not necessarily be the case. So sometimes you may have to carry out a little review of a previous lesson saying, look, in order to be able to understand what I'm going to teach you today, you need to understand these particular points from the lessons that we did a few weeks back or maybe even a month ago, and just simply go through those and just check that they have got an understanding of that. And then, of course, you need to put down an instructional component that's going to describe the sequence of events that make up the lesson. These will include your input as a teacher, and where appropriate, guided practice by the students to consolidate new skills and ideas. So practice that you're going to give them during the course of the lesson. So that could be in the form of questions that you're going to ask them, or indeed worksheets that you hand out to test particular skills that you hope that you've got over to them. If we don't test those skills and see if they have understood them, then we don't know whether they've understood them or not. So it's very important to, during the course of a lesson, to actually test these. And then independent practice that allows the students to extend the skills or knowledge on their own. This may be during the lesson, or it may be, of course, as a homework assignment. And then, of course, when you come towards the end of the lesson, there will be a summary where the teacher wraps up the discussion and answers any further questions that they've got that they haven't asked during the course of the lesson. And then if you're doing a practical, then of course you need to carry out a risk assessment on that particular practical. And an analysis component where the teacher uses to reflect on the lesson itself, such as what worked and what needs improving. So if you find that when you get their homework back in, that every single student is answering a particular question that you set incorrectly, then you may be thinking, well, hang on a moment, why is that happening? Why is everyone, or the vast majority of them, answering this question incorrectly when I'm sure that I didn't, that's not the way I taught it? Could that be a problem that they've got, or could it be a problem that you had in the way in which you presented the information? And you might need to reflect back on that and say, well, hang on a moment, I obviously didn't get over this idea. Is there another way in which I could present it that might be more applicable to the students that I have? Okay. Another very, very important component of chemistry are called practicals. And you'll already have noticed that a certain percentage of marks are allocated to testing experimental skills, knowledge and skills on the two papers. So doing practicals obviously is really quite important. So the specification has actually got 12 core practicals listed. These are listed in italics as specification points. So, for example, 17C, practical, investigate the solubility of a solid in water at specific temperature. You'll notice that it's got a C prefix and it's in italic and it's in bold type. So this is obviously a practical that can only be assessed on paper 2, as indeed can that one, 243C, prepare a sample of pure dry lead 2 sulfate. Some of the other specification points that are linked to practicals are not in bold type and don't have a C prefix, and of course those skills can be assessed on paper 1. So there are 12 of those, and I strongly recommend that the students complete these core practicals in order to develop the necessary skills and understanding of the experiments in order to be able to answer the questions that are going to be set. Because questions could be set directly on a core practical, in which case they could be asked to state how that particular practical is carried out. So they could be asked, how do you prepare a pure sample of dry lead-2 sulfate starting from, and it could be lead-2 nitrate and sodium sulfate solution, for example, or even solids, in which case they'd be said, put them into solution. Or it could be another insoluble solid. They could be told that silver chloride is an insoluble solid. Describe how you could prepare a pure dry sample of silver chloride starting from silver nitrate solution and sodium chloride solution. So there they've got to take their knowledge of Core Practical 243C and apply it to a different scenario. So it's essential that they know the details of those. And secondly, of course, the other thing that's very, very important here is they need to know why they're carrying out each individual stage of a practical. So during the course of this, they need to know why the mixture of the two solutions, after you've mixed them together, why is it filtered? It's a simple one, obviously, is to isolate the solid lead-2 sulfate. They could then be asked, why is that residue washed with deionized or distilled water? In which case, of course, the answer is to remove the remaining solutions that you started with. So it's very, very important that students have got an appreciation of why the individual sections are being carried out, and not only just that a memory of the menu. Okay. Oh, I'm just having a look. There's something in the chat box. Oh. Do you have suggestions of the best web platform to use for core practicals for online students? I'm not quite sure what you mean by the best web practical, but we have got a very, very good practical guide, which I will be mentioning later. That's on the specification on the Pearson qualification website, and I don't know whether that's useful to you. Okay, but I'm not sure about web platforms at all. So sorry, I can't answer that question. Okay. Oh, here we go again. Okay. There are other suggested practicals appearing in the specification. These are optional. However, you may add or substitute your own practicals too, okay? But I will say that the more practical work they do and the more skills that you develop, the better place they are to answer the type of questions that they're likely to be faced with. So what skills are we going to assess in the two papers? The first thing I think perhaps I would like to emphasize is that experimental skills should be embedded with the teaching of the theory. That should say of theory, not or theory. Apologies for my spelling mistake there. So embed practical investigations in the teaching of the theory. So do it alongside the one another. And sometimes it might even be worth doing some practical work before you do the theory to introduce the theory. And I've got an example of one of those later on in the presentation, a practical that I always did before I taught the particular theory. And I'll share that with you later, okay? The development of knowledge and experimental skills can then happen together, which research has shown leads to a secure acquisition of both knowledge and skills. In the assessment of the experimental skills, the students may be tested on their ability to solve problems set in a practical context, apply scientific knowledge and understanding in questions with a practical context. They could be asked to devise and plan investigations using scientific knowledge and understanding when selecting appropriate techniques. They could be asked to demonstrate or describe appropriate experimental investigative methods, including safe and skillful practical techniques. So you need to be talking to them about carrying out practicals in a safe way. So, for example, if you do decide that you've got students who are you're happy to give concentrated sulfuric acid to, and there were a number of students that I taught in the past that I certainly wouldn't have given concentrated sulfuric acid to, but some that I'd be happy to do so. Then your students need to be aware that concentrated sulfuric acid is corrosive and that they should wear gloves, protective gloves. If they are carrying out an experiment in which chlorine is generated, then that must be carried out in a fume cupboard, etc. So discussing these things with them is important. Okay. They may also be asked to make observations and measurements with appropriate position and record these methodically and present them in appropriate ways. There have been questions in which some results have been written down on the exam paper in a very haphazard way, and students have been asked how would what is a better way of recording these particular results, put them into a suitable table with obviously suitable headings and units. They should be able to identify independent, dependent, and control variables. They should be able to use scientific knowledge and understanding to analyze and interpret data to draw conclusions from experimental activities that are consistent with the evidence, and that will be in all forms of experimental work, both in which they're receiving data in the forms of numbers, which could be times or other form of measurements. It could also be, of course, in receiving information of observations about coloured precipitates or gases being given off, etc. They also will be testing their ability to communicate findings from experimental activities, including appropriate technical language, relevant calculations, and graphs. So they should be able to draw the graphs and be able to interpret graphs and be able to do relevant calculations based on the data that they're given. So, for example, they could be given some data regarding a thermochemistry experiment and asked to calculate, say, the heat of combustion from the data. Assess the reliability of an experimental activity, and they could be asked to evaluate data and methods taking into account factors that affect accuracy and validity. Okay, right. Well, we've been going for an hour. So just before I move on to the particular question types and then start looking, perhaps it might be useful for just to have a little 2 or 3 minute break. According to my watch, it is 1 minute to 10 in the UK. So look at your watch and see what your time is. And I will start back at, say, 2 minutes past 10. So just a quick 3 minute break for you to get a drink or a snack or something, or a comfort break of some sort. Okay, so 2 minutes past 10 my time, your equivalent time. Okay, hopefully you're back in front of your computer screens at the moment. Just come back to the question about web platforms. I'm not quite sure about what you mean by web platforms because I'm not the most brilliant people at person at IT. But if you are struggling to actually get the chemicals and the equipment to do some of the core practicals, I would suggest that you go to the Royal Society of Chemistry website and access the teacher resources on the Royal Chemistry of Society website. You can, in fact, sign up on the Royal Society of Chemistry website um, as a teacher to be able to access the information there. And there are quite a lot of useful information and resources available, including some video clips about various different practicals involved. So that might be a useful way in. I'm actually a fellow of the Royal Society of Chemistry, so I've got unlimited access to virtually everything on the website. Um, as a teacher, you can get access to some of the more important aspects that affect your teaching. So, Royal Society of Chemistry. Don't just type in RSC because you might find your first search will be the Royal Shakespeare Company. And although I'm very much in agreement with educating students in Shakespeare, it won't help you very much with your chemistry. Okay, question types. Now, what sort of questions will be set in both papers 1 and 2? Well, there will be some multiple choice, and they will have 4 alternative answers labeled A, B, C, and D. There will be some short response questions with a mark range from 1 up to 4. And there will be some extended writing questions that are worth 5 or 6 marks. And of course, there will be calculations. Chemistry is a mathematical science, and therefore there will be calculations. In fact, there is a stipulated number of marks that need to be awarded to the calculations. Questions assessing experimental skills will be set in both papers. There's a typical multiple choice question, and the students are expected to answer the question by putting a cross in the box next to the letter that they want to be judged by. So in this particular instance, what property of hydrogen makes it suitable gas to use in an airship? They should put a cross next to the letter C. If they had put a cross next to A and later on realized that that actually is not what they want to give as an answer, they put a line through the box and then put a cross in a box they want to be considered for marking. So if they put a cross in A, then they put a line through A and then hopefully put a cross next to C. Okay. They should be spending an average of 1 minute per question. Some of these will be answered in 10 or 20 seconds. They'll answer them very, very quickly in the multiple choice. In general, they should be spending about a minute per mark. Now, if you think you've got a 2-hour paper, that's 120 minutes, 110 marks, then that gives them 10 minutes to go through the paper afterwards and check through to make sure they've answered every single question and make a decision as to whether they want to change something. So that's why I say 1 mark per minute. The 70-mark paper is an hour and 15 minutes. That's a 75 minutes. So they've then got 5 minutes spare at the end to check through. That's in an ideal world, of course, and I do appreciate that the world is not always ideal. There's a typical short response question. It's one that I wrote many years ago. There's the ionic equation given. Use the information in this equation and the particulate collision theory to explain why the rate of reaction decreases in each of the experiments. And the experiments had the concentration of the hydrogen ion of the acid decreasing. So the successive experiments had less and less concentration of acid. And so they're expected, obviously, to say there are fewer hydrogen ions in a given volume, and therefore the number of successful collisions with magnesium atoms are fewer. Okay, so those are the major points to get over there. The next one is they were told that malachites and ore of copper containing copper 2 carbonate and several other compounds that are insoluble in water. They're supplied with several pieces of malachite. Use the chemicals in the apparatus. Describe how you would use the chemicals in the apparatus to obtain a sample of copper from malachite. So they've got to look at the chemicals and apparatus. In this particular instance, they're supplied with a pestle and mortar. So they should have said, grind up the pieces of malachite into a powder. And because they're told they're pieces, so they should appreciate that they're actually solid lumps. Grind it up, okay, then obviously add the dilute sulfuric acid to put the copper 2 ions into solution, add the magnesium powder to precipitate out the copper, and then filter off the copper that you've got and dry it. There we go. Obviously, that's a nice experimental skills question. Here's a typical calculation. They're given an equation. They're told that they react 9.4 grams of copper oxide, show the maximum possible mass of crystals that can be obtained is about 30 grams. They can solve this either by using moles, or they can simply say 79.5 grams will give 249.5, therefore 9.54 will give, and they use mass ratios. I'm a great believer in mass ratios. Some people think you converting everything to moles and then back to grams again is the best way. It's a lot longer, takes them a lot longer in time. Mass ratios are much quicker. I'll leave you to decide which you think is best for your students. And then they're told, I'll give you an answer to an appropriate number of significant figures. You'll see that the minimum number of significant figures is 3. Therefore, they should be given their final answer to 3 significant figures, certainly not 4. If they gave the answer to 2 significant figures, I personally would accept that as well. And some mathematicians will argue that 2 significant figures is more appropriate than 3. So if I was principal examiner for this particular question, I would have accepted a final answer to either 3 or 2 significant figures. To be on the safe side, 3 significant figures, because that's the minimum number of significant figures given in the data. In this experiment, the actual yield was 23.92. Calculate the percentage yield. So can they calculate the percentage? Simple. Um, okay, so another activity for you. Hydrogen iodide can be manufactured from its elements using that reaction. So the student should be looking at that reaction and saying, right, well, look, there's a gas phase reaction that's reversible. It can reach a position of equilibrium. Uh, there's the same number of moles on either side of the equation, and it's exothermic in the forward direction. Okay, now what other information have they given me? Notice how I would expect a student of mine to be looking at that and looking at that equation and the information given before they carried on reading the rest of the question. This is something I tried to train my students into doing. Now, a temperature of 500 degrees C and a pressure of 4 atmosphere and a platinum catalyst are used in this manufacturing process. But a manufacturer carries out this reaction using the same catalyst, a pressure of 4 atmosphere, but decides to use a temperature of 400 degrees C rather than 500. So the question is, state the effect of this change on the yield of hydrogen iodide and justify your answer. So jot down on a piece of paper or keep in your head, what do you think are the two essential points to include when answering this question? And remember what I've said earlier about answering questions on the effect of variables on the position of equilibrium. So first of all, state the effect and then justify your answer. Okay, for this reaction, it is sufficient to say a decrease in temperature increases the yield. In fact, all the student would have to write down is increases. They don't have to write out that full sentence, just increases, 1 mark, because the forward reaction is exothermic, 1 mark. Forward could be in brackets. If they just simply said because the reaction is exothermic, that's okay. All right. If they had to, however, in another experiment, have to refer to the reverse reaction, if they wanted to say because the reverse reaction is endothermic, that still would have, of course, scored the mark, but they would have had to put in the word reverse. The reason why they don't have to say it's the forward reaction is exothermic is because it is standard practice to quote delta H for a reversible reaction for the forward reaction. So forward is not necessary if they're referring to the forward reaction. Now note that that's all they've got to say. They don't need to make any reference to Le Chatelier's principle. It's not needed and should not be used. Now, once again, I want to stress, I'm not here to tell you how to teach your students. If you want to use Le Chatelier's principle because you think it may help your students to appreciate what's happening, please go ahead. But do be aware that they are not going to get marks for making any reference to Le Chatelier's principle or the principles behind Le Chatelier's principle. So don't use the word twice. And please be aware that in my experience of marking examination papers for, what was it, 1984 through to 2017, that's over 30 years, the number of times I've seen students try to use Le Chatelier's principle and come up with conflicting information that loses them the marks is enormous. I've seen it many, many, many times. So I would very strongly suggest that even if you decide to put Le Chatelier's principle into your teaching, that you make it very clear to your students that they shouldn't be using that principle when that's an examination question. Now, this applies to both international GCSE and international A-level. Okay, very important. Okay, activity 5. What are the 5 essential points to include in answering the following question? Describe how a pure dry sample of hydrated copper 2 sulfate crystals can be obtained from a dilute solution of copper 2 sulfate. Usually, this question is the last part of a question in which they've been the question's all been about adding copper 2 oxide in excess to dilute sulfuric acid, to hot dilute sulfuric acid, or warm dilute sulfuric acid, filtering off the excess copper oxide, and then you've got your dilution of copper 2 sulfate. And how do you get a dry sample of hydrated copper 2 sulfate crystals from that particular solution that you've got at the end? Okay, so you might want to just jot down those or just keep them in your head. Okay. Okay, hopefully you've had a chance to give some thought to that. Here, this is what I consider to be the simplest way of answering this particular question. There are a number of other alternatives, and when you come across the answers in a mark scheme to this, you'll see there are quite a number of alternatives. But I think this is the simplest way of answering this particular question. Heat or boil the filtrate until crystals form in a cooled sample. Leave the solution to cool so the crystals form. Filter to remove the crystals. Dry the crystals on filter paper. One of the questions I am often asked is, can we put this down as I've done here? Yes, providing, of course, you've got each particular point in order. So you need to be consequential here, okay? So bullet points can be answered in extended response, they can be used in extended response questions, but they need to be sequential. They need to be, one follows on from the other. So they need to be in the right order, okay? One other thing is that I remember quite some time ago, when I was principal examiner and I had a question like this and I had my team leaders in front of me, one of my team leaders said, how many marks are you going to give for leave the solution to evaporate to dryness? Because that will give them copper 2 sulfate crystals. And I said, 0. And they said, why 0? Why no marks whatsoever? And I said, well, because we do not know if the copper 2 oxide that you started with was pure or impure. And it might have been impure. And some of those impurities may have been soluble in water, in which case they will be carried over into the filtrate. And if you just leave that solution to evaporate to dryness, then those impurities will also crystallize out along with the copper 2 sulfate. And so therefore, you are not getting a pure sample of copper 2 sulfate. And I remember her saying, well, that's very harsh. and then saying, well, sometimes life is harsh. So that's the reason why the students shouldn't just say, leave the solution to evaporate to dryness. However, having said that, there are some occasions in which you cannot use this technique in order to get a pure dry sample of a solid from a solution. An example is sodium chloride, because the solubility of sodium chloride in hot water and cold water are almost identical. So if you got a hot saturated solution of sodium chloride and left it to cool and crystallize, there would be hardly any sodium chloride to crystallize out. So in those occasions, you would have to evaporate to dryness. So it depends on whether or not you've got a substance whose solubility is different. And whilst I'm on this particular experiment, the students should also appreciate not only that this is what you do, but why each stage is carried out and why it works. So why are you heating and boiling the filtrate until crystals form in a cooled sample? And the answer is, of course, you're trying to get a hot saturated solution. Why, when that solution is left to cool, why do crystals form? Because the copper sulfate is less soluble in cold water than it is in hot water. They need to know that because they could be asked it. Okay. Why would you not dry the crystals in a hot oven is another justifiable question. And the answer would be, of course, because you would dehydrate the crystals. They should know that when you heat hydrated copper to sulfate crystals, they turn into anhydrous copper sulfate. So some useful information they need to know. So I remember when I first started doing practicals back in 1973, when I was only 22 years old, and didn't know as much about teaching as I do now. When I got the students to do practicals, I thought, this is time out for me. I'll get a cup of tea, put my feet up on the table and let them get on with it. In the days when we could have cups of tea in the laboratory. You can't these days because of health and safety rules, of course. Now I realise that it's much more important for me to go around and start quizzing them about the question, why are you doing this? Because it says so on the sheet you gave me, Mr. Curtis. Yes, but why did I say to do that? And start seeing if they appreciate why they're carrying out the experiment, as well as do they remember what they're doing. Okay, right, enough about practical work for the moment. Then let's have a look at these assessment objectives and why do I think they're so important for both you and possibly even your students to have an appreciation of. First of all, why do we have them? Well, to help make the exams fairer year on year. One of the ways we do this, of course, is because if you remember from earlier slides, there are a certain number of marks allocated to each of the 3 assessment objectives. And because they're within those parameters every single year, then one exam should not be any more significantly different in terms of difficulty and demand from one year to the next, because we're keeping the marks within those particular framework. It also, of course, provides a structure for question paper writers because they have to write questions that fall within those particular parameters. There has to be a certain number of percentage marks allocated to AO1, AO2, and AO3. And to make sure the exam is about skills and not just about knowledge, we'll see the difference once again between AO1, AO2, and AO3 in a moment. And I think you'll quickly spot that a number of the questions are about skills and not knowledge. And it does provide both you and your students about some reassurance about the types of questions that will actually be asked, because you know there are going to be a certain number of percentage questions on AO1, AO2, and AO3. So what are they? Well, AO1 is all about knowledge and understanding in chemistry. So there are a lot of statements in the specification that simply say the student should know that. And therefore, the examiners are perfectly entitled to say, state what is meant by. When it's in the specification, students should know that. Basic understanding, very, very simple understanding. That's not complicated. Okay, so something that's actually in the specification. AO2, however, is about application of knowledge and understanding, analysis and evaluation in chemistry. So this is where they take the knowledge that they've acquired and the understanding that they've acquired and they apply it to an unfamiliar situation. AO3 is all about experimental skills, analysis and evaluation of data and methods in chemistry. And we'll get a better understanding, I think, of the sorts of questions that are set when we start looking at the student responses and the mark schemes and getting you to have a look at marking some student work. Okay, so the questions in AO1 require the students to recall and use information that you have in fact effectively taught them. Okay, state what is meant by enthalpy change of combustion. Yeah, it says in the specifications, a student should know what is meant by enthalpy change of combustion. So they should be able to recall that and use that information. AO2 requires questions requiring students to apply what you've taught them or to use the skills or the analysis to make judgments. So the skills that they've developed and the ability to be able to analyze and make judgments based on all the work that you've done with them should enable them to be able to provide them with the skills necessary to be able to answer those types of questions. And AO3, of course, a question on the practical work, associated practical skills such as planning, drawing graphs, analysing data, and evaluating methods, to name just a few. And remember that you approximately 40% of the marks to AO1, 40% of the marks to AO2, and 20% of the marks to AO3. And that's got to be the same through papers 1 and 2, and it's got to be same for one session after another. Compared to the previous specification, the new specification has less AO1 and more AO2. So we're concentrating more on skills now than we were in the previous qualification. So what would typical AO1 questions be? Simple recall, or can be based on straightforward understanding and not just knowledge. Typical AO2 questions can involve simple ideas being applied to unfamiliar scenarios, or can involve more complex scenarios involving data analysis or evaluation. And we'll see quite a number of examples of this in a moment. Typical AO3 questions, questions based on practical experiences, not just the core practicals, but any practical work, but obviously related to the skills they've developed as a result of doing or seeing the core practicals performed. So, for example, here we've got sodium chloride is a soluble salt. Name the acid and the alkali that can be used to make sodium chloride. And then a teacher drops a bottle containing sodium chloride. The bottle breaks when it hits the floor. The teacher sweeps up the mixture of sodium chloride in glass. Describe how the teacher can obtain a pure, dry sample of sodium chloride from the mixture. Again, this is a question that I wrote quite some time ago. And when I originally wrote it, I had it, the student sweeps up the reaction mixture, describe how the student can obtain a pure, dry sample. And I was told that because of health and safety regulations, I shouldn't have students sweeping up glass. So I had to change it to teacher, which I found quite amusing, but there you are. Okay, so here, what we're asking, and what we're testing here is that the student should know the sodium chloride is soluble in water and glass isn't. I hope they know that glass isn't soluble in water because they've been putting water into glasses, drinking glasses at home and into beakers in the laboratory. So they should add water to dissolve up the sodium chloride, filter off the solution so that you separate out the glass, and then evaporate the solution to dryness. Remember, sodium chloride has a similar solubility in hot water and in cold, so you can't create a saturated solution in cool to dryness. You have to evaporate it completely to dryness or leave it to evaporate on its own to dryness. Okay? Right. Okay, so now we get on to the nitty-gritty. First of all, assigning AOs to various questions. Okay, so if you've got access to your specification, which you might have a hard copy in front of you, or you can bring up onto the screen from the downloads, the delegate downloads. I'm not sure whether in the left or right hand corner of your screen, you can bring up the specification on a temporary basis, and you can. Oh no, no, you shouldn't need to. You don't need the specification. Ignore that. I'm talking rubbish. All you need is a knowledge of the three types of specification. AO1, knowledge and basic understanding. AO2, application. AO3, experimental skills. So there's that one. Okay. What's the colour of the flame test containing lithium ions? AO1, AO2, or AO3? Now, when deciding whether it is AO1 or AO2, you have to have a knowledge of the specification itself. So you need to ask yourself, are the students expected to know the colour of the flame in a flame test when the compound contains lithium ions? And the answer is yes, they are expected to know it's red, and therefore it is AO1. There's the second one. Are the students expected to know the formula of ammonium carbonate? Is that mentioned on the specification? The student should know the formula of ammonium carbonate. Is that on the specification? If it's the answer is yes, it's AO1. If the answer is no, it's AO2. And of course is it's not on the specification, so it is AO2. But how are they expected to work this out? Well, what is listed on the specification is the formula. They're expected to know the formula of the ammonium ion, and they're expected to know the formula of the carbonate ion. So then they apply those two formulae to work out the correct formula for ammonium carbonate and come up with, hopefully, the answer D. Okay. 3 parts to this particular question. State what is meant by the term exothermic, state why aluminium displaces iron, and explain why this reaction is a redox reaction. And the questions to ask yourself is, are they expected to know this information from the specification? Answer, of course, for exothermic is yes, they are expected to know this. State why aluminium displaces iron, but they know the reactivity series because that's listed on the specification. What's also listed on the specification is they are expected to know that an element higher in the reactivity series displaces one that is lower. So that is actually AO1. You could argue along the lines AO2, and some of my team leaders would have suggested that's possible. Some of the team would have suggested that maybe AO2, but it can actually be classified as AO1. And are they expected to know what is meant by reduction and oxidation, and hence be able to state that as a redox reaction? And the answer is yes. So that is in fact AO1 as well. Again, you could make out an argument that that's AO2 because they're applying it to a specific reaction. But they should know that the iron 3 oxide is being, they should know that this is a redox reaction because both reduction and oxidation are taking place. And that's what a redox reaction is. Okay, yeah, and that says the student should know what is meant by a redox reaction. It's one in which both oxidation and reduction is taking place. Okay, there's 2. There's the top question, explain why the student needs to clean the platinum wire, and then the bottom one's a calculation. So what's the top one first of all, and then the calculation for the bottom one. Well, the top one's obviously linked to a practical. So it's linked to a practical procedure. It's linked in the platinum wire, so it's AO3. The bottom one is a calculation, and calculations are AO2. Next, a technician finds an unlabeled bottle on the shelf that could be ammonium carbonate solution. Describe tests that the technician should do to confirm that solution contains both ammonium ions and carbonate ions. The temptation here is to assign this to AO3 because it's linked to a practical procedure. However, this is straightforward recall from the specification. The students are expected to know the test for the ammonium ion and the test for the carbonate ion. So it's actually AO1. So all 6 marks here are AO1. Interesting, eh? Teacher adds a small piece of sodium to a trough of water. I prefer water contained in a trough. I can't see how you can make a trough out of water, but never mind. That's just me being pedantic. Give 2 observations that are made when sodium reacts with water. And after the reaction is stopped, the teacher adds a few drops of phenolphthalein solution to the solution in the trough. Explain the color of the phenolphthalein after it's added to the solution. So part 1, first of all, give 2 observations that are made when sodium reacts with water. Does the specification actually state that the students are expected to know the observations made when sodium reacts with water? The answer is actually no. Then it's not specifically stated the observations that are made. It does say that they should have a knowledge. They should be aware of the reactions of lithium, sodium, potassium with water, but it doesn't specifically state that they should have a knowledge of the observations. But of course, they will either see these performed, or if you've got very good students, you can give them very tiny pieces of lithium, sodium, potassium, and put them on a little piece of filter paper and get them to drop that into a large beaker with water. That depends on how good your students are, but they should see them. So actually, part 1 is AO3. After the reaction stopped, the teacher adds a few drops of phenolphthalein solution to the solution in the trough. Explain the color. Well, the first thing, of course, they've got to do is they've got to say to you, now, what color does it actually go, and why does it go that color? So the explanation of why it goes that color is AO1, because it's a knowledge that the color change, stating the color change, is AO3, but the explanation of the color change is AO1 because they're expected to know that the solution formed is alkaline, and alkaline solutions are pink and phenolphthalein. So that's AO1. So notice within a particular part question, 2 different assessment objectives are being assessed. So don't necessarily think that any given question is assessing just one assessment objective, or indeed sometimes even a part question is assessing exactly one assessment objective. Sometimes there's more than one. Now, there's one other aspect to all of the questions that are set on question papers, and that is the use of command words. Every single question, in inverted commas, on a question paper these days, on an exam paper, is not really a question, it's a command. Do this, do that, do the other. The only time questions can be asked are in multiple choice questions. So you will see specific questions, specific command words used, like give, name, which are used to test simple recall, describe, which is to use in knowledge, giving reasons, explain. So they're not actually asking the question, they're commanding the student into a particular answer. Provide more detailed analysis, the command word will be evaluate or justify. Show particular skills, calculate or plot. I'll just emphasize that explain one here, because the explain one is quite important, because explain could include a statement as well. Many years ago, when we were writing exam papers, we were able to use two command words in the same question. So we could say state and explain. Now that is now not allowed. We can only use one command word in any particular sentence in the question. So the question, the use of the word explain could be a straightforward explanation, but could involve a state as well. So for example, if the question said, explain why the rate of the reaction increases with an increase in concentration, say the reaction between magnesium and hydrochloric acid increases with an increase in concentration of hydrochloric acid, all they have to do is explain. But the question could say, explain how the rate of the reaction changes with an increase in concentration of hydrochloric acid. In this case, they have to say, first of all, the rate of the reaction will increase, and then they offer the explanation. So the word explain could be state and explain. Okay. Another one that's important is the difference between deduce and determine. They look at face value as if they are the same, deduce, determine. And in everyday language, they might actually mean exactly the same thing, but not in exam questions, because determine differs from deduce in the sense that there has to be an element of quantitative answer in description in your answer. So that could be just a straightforward calculation or use of numbers in some way to explain your answer. Now, how do you find out the difference between all of these and what each one means? Well, in the specification that you have got, there is in the appendix, and I'm not sure which appendix number it is, but there is a use of a list of all the command words and what they entail. And one of the things I used to do with my students is I directed them to the Pearson qualification website, and I directed them to the International GCSE section of the qualification website, then to the chemistry section, and then to the specification, and then say, right, download from that the list of all the command words, and then print them out. And it would come onto 2 sheets of paper, and I said, I want you to put those 2 sheets of paper in the front of your folder. And every time you come across a command word, I want you to look at that sheet of paper and see what you have to do to answer the question using that command word. And as they went through their course for the 2 years, they gradually got used to what every single command word necessitated. And it's something perhaps you might like to think. Now, is there a link between command words and AOs? Well, there's, I think, a little bit of a list. I think, for example, add or label, describe, explain, give, state, name, or give a simple reason falls into AO1. Things like calculate, identify, deduce, determine, predict, suggest, or write an equation comes into AO2. Deduce, design, draw, estimate, plot, evaluate, where deduce and design are associated with experimental work, falls into AO3. So that's not an exhaustive list, that's just a few suggestions. So why do I think that's useful? Well, I think it's quite useful for students to appreciate that what type of questions are associated to AO1 and AO2. And the use of the command words might actually give them a little insight. Now, why do I think that's so important? Well, we're going to have a look at some AO2 questions in mark schemes, but you may be asking why I'm not looking at AO1. And that's because it's all about knowledge and basic understanding. It's not one that you can influence very much unless you've got the time to constantly test their knowledge, which in the time frame that you're given to teach a specification, I doubt very much if you can do record tests that often. So the students either go away and learn what you teach them or what's on the specification from the students should know statements, or they don't. And there's not a lot you can do. We have a saying in the UK, you can lead a horse to water, but you can't make them drink. But remember that students should still recognise AO1 questions and not spend time going beyond AO2, beyond AO1. So just because in an AO1 question that's worth 2 marks, there's been 4 lines of answer lines left, doesn't mean they have to fill all 4 lines, because it's an AO1 question and it's straightforward, simple, basic understanding, and they shouldn't be trying to fill all 4 lines. The reason 4 lines are left is because if they make a mistake in their first 2 lines, which is what they should need to answer the question, they've got room to cross it out and they've got another 2 lines to put their answer in. And that's the reason 4 lines have been left for a 2-mark question, not because we're expecting them to fill all 4 lines. So try to encourage them not to go into excessive information for AO1 questions. So now I'm hoping you're getting the appreciation of why I think it's a good idea that students should be aware of what type of questions are targeting AO1. So let's have a look at some typical AO2 questions before I get you to do some marking of AO2 questions. This one that we looked at earlier of explaining why the new equilibrium mixture contains less NO2 than the original equilibrium mixture obviously is AO2 because it's an application of their knowledge and understanding of the effect of variables on the position of equilibrium and applying it to an unfamiliar situation. Calculations, AO2. I like this particular calculation because it says show by calculation the empirical formula is, which means they have to show their calculation work. They can't simply say, "Oh, I did my calculation on my on my I can't even think of the word. Oh, don't get old, guys. On my calculator, and it came out to it came out to 1 to 1 to 3. They have to actually show their work. And why is that important? Well, because in other calculations where they don't necessarily have to show their calculation, if they get the correct answer without showing their working, they can actually get full marks. But on these, they have to show their working. So that's why I quite like those. Okay, write a chemical equation, that's typical AO2. You could argue that very simple equations, let's say carbon plus oxygen given carbon dioxide, is so simple and straightforward that that's basic knowledge. You could argue that's AO1. But something slightly more complicated that needs a little bit of balancing is really AO2. Draw and dot and cross diagram for an unfamiliar situation, unfamiliar molecule. So this is one I set quite some time ago. I gave them the structural formula, the displayed formula for it. They should be aware that each line represents a shared pair of electrons, and therefore they should be able to work out that you have to have one shared electron from each fluorine and carbon, from electron from fluorine and electron from carbon to form each of those shared pair of electrons, and one from a bromine and a carbon to form the other shared pair of electrons, and then show all the non-bonding electrons on the fluorine, 3 fluorines and the bromines. If it had said draw and dot cross diagram to show the outer electrons in methane, then of course that would be AO1 because that's on the specification. but this one isn't on specification. You notice I was very careful to say that the lines do not represent bonds. A bond is an electrostatic force of attraction. You can't represent an electrostatic force of attraction on a piece of paper. You can only represent a shared pair of electrons on a piece of paper by a line. That's me being pedantic again, but there you are. Interesting, eh? Okay, so now over to something for you to do. Use the mark scheme shown on screen to mark the student responses on slides 70 to 84, and we'll go through each question one at a time. Now, here is where you might want to jot down the actual answers to each one of the questions, because you may decide that you want to use these with your students. So you're quite at liberty to use these student responses and get them to mark them, and then you can compare the actual marks with them, and I think you'll see that there's some. I've chosen examples quite carefully to highlight specific points. So here's the first question. Nitrogen dioxide produced in car engines reacts with water vapor and oxygen in the atmosphere to form nitric acid. Give a chemical equation for this particular reaction. So the equation we expect them to write is the one that's given there. And there are 2 marks allocated. The first mark, M1, for all formulae being correct. The second mark is for correct balancing of the correct formulae. Allow in the notes column, allow multiples in fractions, ignore state symbols even if correct, because state symbols haven't been asked for. So we're not testing state symbols, so just ignore them. But note M2 is dependent on M1. They have to get the formulae correct to be able to score the second mark, which highlights something I mentioned earlier about making sure students can write correct formulae. And I'm a great believer in actually testing this on a regular basis. You could even do it as a, say, every month as a 10-minute opening to a lesson. Give them a whole sheet of names of compounds and ask them to write the formulae for 10 minutes at the beginning of a lesson on a regular basis, say once a month, once every 2 months, whatever you feel. It's so important. Okay, so there's the first one. How many marks allocated to that particular answer? Right, well, the first thing you do is ignore the crossed out work because it's been replaced. So look at the replacement and it is correct for 2 marks because you can allow multiples. Student 2. Correct equation. Ignore the crossing out in front of NO2 and look at the replacement, and it's the letter 4. So it looks like either 3 or 5 has been crossed out. So ignore that and look at the 4. So that's now a correct equation, and you can award both marks because it says in the notes column, ignore symbols even if incorrect. So 2 marks. You can see now why I'm picking these specific examples and why it might be useful for your students to see some of these. Up to you. Student 3. Right? There's no marks there because, of course, you can't give M1 because it's an incorrect formula for oxygen. And although it is correctly balanced, you can't give the M2 mark because it's dependent on M1. They have to get the M1 mark. They have to get everything correct. So this student knows how to balance an equation, but gets no marks at all because they have to get all the formulae correct. And that is common practice at both GCSE and A-level. So the students need to be aware that it is so important that they get formally correct. Student 4. Two marks, allow fractions. In the notes column, allow multiples and fractions. Okay? Again, up to you whether you want to use these with your students. Okay, the next one, describe a test for chlorine. Okay, so a description that refers to the following 2 points. Litmus paper and is bleached or turns white. Ignore gas or solution. Okay, so you notice use damp blue is in brackets. So they didn't have to say that it's blue litmus paper that they're using, just litmus paper. Okay, and bleached or turns white. Now let's have a look at the notes column because there's quite a lot there. Allow universal indicator paper, fine. Accept blue litmus paper turns red and is then bleached because, of course, chlorine solution is slightly acidic. Ignore gas or solution, which appears in the answer column as well. I'm not quite sure why it's in the answer column, but never mind, there's no harm done. This is not going to crop up, but notice that they would allow bromide solution turns brown, reject iodide solution. M2 is dependent on M1. Red litmus paper turns blue, then bleaches, turns white, scores M1 only. Because, of course, red litmus won't turn blue. But they're being generous because red litmus paper will, of course, bleach. So if they say red litmus paper bleaches, they go 2 marks. But if they put in it turns blue before it bleaches, then obviously that's incorrect science, and therefore only scores 1. Okay, so apart from the business about bromide and iodide solutions, which is not going to crop up in our answers, focus on the note, everything that's in the notes column as well as what's in the answer, because the notes is going to crop up. Right, there's student 1. So litmus paper 1, bleach, M2, 2 marks. Second student. At the very bottom of the notes column, quite clearly states, red litmus paper turns blue, then bleaches, M1 only, so 1 mark. Student 3. M1, litmus paper, M2, turns white, 2 marks. Work crossed out but not replaced must be marked. That is an off-qual regulation. Off-qual is the government-appointed apartment that oversees all assessment in UK examinations. And in order to make sure that the international exams set by Pearson Edexcel are taken as equivalent to UK examinations, both at GCSE and A level, then Pearson apply off-qual regulations to the marking of international papers, qualifications. So, and their statement, off-qual statement, is that work crossed out but not replaced must be marked. If it is replaced, you ignore what's crossed out and you look at what it's replaced. So if they had crossed that lot out and then put down something that was incorrect, they would have scored no marks at all. Okay, student 4. 1 mark for universal indicator paper because it says allow universal indicator paper. And then on the bottom line, they've got it bleached or turning white. So 2 marks because you can allow universal indicator paper. Okay, there's the third one, and we've just gone past the hour mark again, and I suggest we just have another little break for about 2 or 3 minutes. It's 1 minute to 11 on my watch. So have a look at the time on your watch or computer screen, and let's say another 3 minutes. So that's 2 minutes, 7 minutes past 11 on my watch, okay? And we'll start up again then. Okay, it's 2 minutes past 11 by my 7 minutes past 11 by my watch. So let's pick up again. Here we've got another question. You've got a sample of element X contains three isotopes, and you've got the percentage composition of protons, neutrons, and relative abundance. And you're asked to use the information in the table to calculate the relative atomic mass of element Z and give your answer to one decimal place. So the mark scheme is split up into four different parts of the calculation. The first one is for actually using the correct isotopic masses of 24, 25, and 26. Then the second mark is for multiplying them by their correct percentage abundances, 79.0, 10.0, and 11.0. Or if they decide that they don't want to put all that down on paper and they simply write down 2,432, okay, then that 2,432 will, of course, or the showing of the calculation will, of course, get them the first 2 marks. Because if they worked out 2,432, they must have used 24, 25, and 26. Okay, the third mark is for dividing by 100 or coming up with the answer 24.32. Well, if they get the answer 24.32 and that's all they've written down, they must have done part 1 and part 2 and part 3 of the calculation. So that's worth 3 marks. We'll have a look at the notes column and confirm that in a moment. And the last mark is for taking their answer from M3 and putting it to one decimal place. We are testing here the ability of a student to give an answer to one decimal place. So M3 does not have to be correct, but if they then take their answer from M3 and give it to one decimal place, then they can score M4. Okay, hope I've made that clear. If they get the answer 24.3 and that's all they've got, then obviously they must have done the calculation correctly, so it's worth 4 marks. They don't actually have to show their working. Now let's see if that's what it says over there. Well, in the notes column, it says M2 subsumes M1. Well, that's what I said. If they get 2432, they must have used 24, 25, and 26. Allow an error carried forward if incorrect mass numbers used. So, for example, 12.3 scores 3 as long as they show some work in. So I assume that that means that they've used 12, 13, and 14 as opposed to 24, 25, and 26. Okay. 24.3 without working scores 4 marks. So that's final answer without any working, scores all marks. That again is an off-call regulation. 24.32 without working scores 3. And M4 scores only if the numbers from the table are used. So if they've used the numbers from the table, but they've done the arithmetic wrong, and they've come up with an answer in M3 that is not the correct answer, but they then put that to one decimal place, they can get M4 as a sort of rescue mark. Okay, I hope that's clear. So let's have a look at the student responses. And that shouldn't take any time in marking whatsoever, because of course you can see 24.3 in the answer line. That's the correct answer. So they must have done everything correct. And they have, of course they have, because that's M1, that's M2 and M3, and that's M4. So 4 marks. Nice simple one for the examiners to mark. And we always tell our examiners, if the final answer is correct, it's odds-on favourite that they've done the calculation correct. I keep having examiners tell me there could be compensating errors. Yeah, by all means, look to see if there's compensating errors. I must admit, in over 30 years of marking, I've never seen a correct answer that's got compensating errors in it. But I've been told that some of my examiners have seen that. Okay, there's the next one. I'm sure you've noticed straight away that that's worth 3 marks for 12.3, scores 3 with working. It's in the notes column. Student 3. $24.32 without working, scores 3. So 3 marks for that. It's in the notes column. Last but one. Last student. No marks. Incorrect answer with no working, score 0, which is pity because they must have done the correct working on their computer, on their calculator, and then decided that the final answer to 1 decimal place is 24. And it's not. It's incorrect answer. So they score 0. Okay, and that's a good one to show your students because they must have done some correct working on their calculator. And if they'd shown that correct working, they would have got 3 marks. But unfortunately, they score 0. And if that doesn't emphasize to your students and convince them that they must show their working, I don't know what will. And there's nothing you can do to help them if they decide to ignore your advice about showing working. They're a lost cause. Okay, preparing students for AO2. Right, this is just some things for you to consider in your own time, really. Okay, we're not going to have a long chat about this. If we were face to face, perhaps we could have a little bit of a chat, but with the large number of you that are in the room at the moment, obviously it's not practical to have conversations over the web on this. So there's some things for you to think about, but I'll give you some suggestions. Is it better to present facts or to teach principles, and why? Well, AO2, of course, is all about understanding and applying your knowledge and applying your understanding to unfamiliar situations. And so obviously teaching principles rather than facts are more important. However, if we're answering AO2 questions, but however, I used to have a teacher who used to say to me, Curtis, you can't think in a vacuum, boy. And the point he was trying to make to me was that you have to have a lot of knowledge in order to be able to apply that knowledge. And you have to have understanding in order to be able to apply that understanding. So presenting facts and basic understanding is incredibly important, but preparing students for AO2, you've got to spend considerable amount of time teaching principles. Questioning styles. So when you're in the classroom, is it better to ask closed or open questions, and why? Well, if you're trying to test recall, closed questions where there's just simply one answer is fine. But if you're trying to test their understanding, you need to ask an open question. The one I always ask at A-level, and it's not, of course, applicable to GCSE, but I can't think of one at GCSE right at the moment, is what is the name of the catalyst in the Haber process? Iron. Good, close question. How does the catalyst in the Haber process work? Open question. They then have to go through and think through all the various stages. So it's that sort of thing. Okay. Assessment activities. Is it better to assess formative or summative assessments, and why? Summative assessments are where you are solely interested in how they performed in terms of the numerical outcome. How many percentage marks have they managed to get right? How many marks out of 20 or 50 or 100 have they managed to get? That's it. That's a summative assessment. And sometimes summative assessments are useful because you can put them in rank order and you can use them to put them into ability sets if that's what your school does. Exams are summative assessments. We put them in rank order and we say that a certain percentage are going to get grade 9, and a certain percentage are going to get grade 8, and so on. So they're summative assessments. Formative assessments are where you have specifically set the assessments with the aim of giving them feedback to what they have done well and what they haven't done so well, and how perhaps they could improve the next time that they're faced with similar questions. So it's pretty obviously formative assessments are much better. So consider trying to build in as many of those types of assessments as you can. And with exam preparation, what else could you do to prepare your students to answer AO2 questions? Well, you can go away and obviously have a think about that amongst either yourself or within your departments. One of the things you could do, of course, is to try and give them as many AO2 questions as you can, and you can use Exam Wizard to do that. I'll mention Exam Wizard a little bit later because it's one of the things that we've developed at Pearson's to help you and support you. Okay. Something else for you to think about when you leave this presentation, think about one of the topics that you teach, which often has AO2 questions in exams. And again, you can use Exam Wizard to find out those types of questions, but also looking at the questions, it's pretty obvious which are AO2, which are AO1. So think of, and you can build up the type of topics that are often AO2 questions are set. Obviously, things like rates of reaction, energetics, equilibria, those are very common topics. Okay. When you're teaching this, what sort of questions do you ask? By the time I'd been teaching towards the end of my career, I could just simply walk into a lesson, teach a particular topic, and I knew what questions I was going to ask because I'd taught that topic so many times in the past, and I'd built up a bank of questions, and I knew exactly what I was going to do. I didn't need lesson plans in those days. By the time I'd been teaching for 20, 30 years, certainly by the time I'd reached my 30th year, I didn't. If you're a bit newer to teaching or you've been assigned a particular topic to teach that you haven't taught before, it's well worth your while thinking about what sort of questions should I be asking when I'm trying to develop the skills for them, my students, to be able to answer AO2 questions on this particular topic. How do these questions help my students prepare for AO2 questions? Yeah, so are you definitely asking the right types of questions? And if you're not sure, have a chat with your colleagues. If you have got colleagues, okay? I remember once someone was asking me about a new member of my department, and I was asked her, how is she settling in? And I said, she is settling in very well. She's already asking questions, which I am very, very about how to teach something. And I said, I am extremely impressed with someone who comes to me and says, how can I teach this? Can you give me some help? That to me was a very, very plus sign for that particular member of my department who was new in. Don't be afraid to ask your colleagues questions. And okay, other things for you to think about after this session. Why do you set homework? When I started teaching in 1973, I was told you must set homework. So I set homework. I never gave any thought to why I was setting it or whether it was any use to them. I set it because I was told I had to. I soon learnt that there was a hell of a lot more for my students to gain from setting the right type of homework. So what sort of questions and problems do you actually set, and what do you expect the students to gain from those questions that you set? Do you give sufficient thought into those questions? Yeah. If the answer is yes, well done. Okay. If the answer, like me in 1973, was no, not so good. Will they gain? What will they gain to help them answer AO2 questions? Okay. Right, so now we move on to AO3. What is AO3? Well, remember, it's all about assessing practical skills and understanding that they gain from the practical work that they do. Remember that the questions may require recall of practical techniques of the core practicals, the 12 core practicals, but it may also require application and understanding of these to new situations. And it may involve the use of experimental data and the evaluation of experimental methods and results. So there's a recall of a practical technique. Describe how the student could obtain pure dry sample of hydrated crystals from the filtrate obtained in stage 6. Stage 6 is where they filtered off the excess copper 2 oxide to get a dilute solution of copper 2 sulfate. Okay, that's a recall of a practical technique. It's taken from statement 2.42 from the specification. The practical, prepare a sample of pure dry hydrated copper 2 sulfate crystals started from copper 2 oxide. Okay, so that's actually a core practical. So it's a recall of a practical technique. Analysis of results. The graph on the next slide shows the results of reacting two different acids, X and Y, with the same mass of magnesium ribbon at the same temperature. Explain how the curves show which acid has the greater concentration of hydrogen ions. And there's the two graphs. And remember, the question says, explain how the curves show which acid. So one of the ways of answering this question is to say X has the greater concentration because the curve has a steeper gradient, showing that the reaction takes place more quickly. Another way of answering it would be to actually use the data from the curves to say, for example, after 20 seconds, you get 12 cubic centimeters of gas collected with X, whereas you only get 6 cubic centimeters of gas collected with Y. So you're getting more gas given off with X than with Y, so that must be the greater concentration. Actually have to use the curves. Okay, so if you're going to go down the route of using the gas given off, more gas given off, you need to state the actual figures. Okay, evaluation of methods. There's an experiment where you put some magnesium ribbon into a conical flask, add the acid and collect the gas given off. The expected volume of gas produced in the experiment is 86, suggests why the volume collected is less than the expected volume. Of course, what happens in between adding the acid and replacing the bung is some gas is lost. So they should be aware that that's the case. The student uses a graduated beaker to measure the volume of dilute hydrochloric acid. Explain why it's not necessary to use a measuring cylinder. Well, the acid is in excess. So why do you need to measure it accurately? You don't. Measure it precisely. You don't need to measure it precisely because it's in excess. So an approximate volume is perfectly acceptable. Okay. Next, look at, because evaluations are so badly answered, here's the examiner's report on that. In question C, the question was poorly answered by the majority of candidates. Many said that gas escapes or is lost, but very few of those went on to say why it escapes. So that's insufficient toward the mark. They had to say why the gas escapes. Some said that the magnesium did not fully react, which is not creditworthy because the acid's in excess. So there's no reaction, no reason why the magnesium was not reacting. In question D, this question was not particularly well answered. Many talked about an accurate measurement not being required. Should have said precise measurement, but never mind. Not being required, but failed to mention that this was because the acid was in excess. As the second marking point was dependent on the first, answers such as these could not be awarded. Okay, use of data. The table below shows the results done by four students, A, B, C, and D. You explain how the results show that the alcohol evaporates most easily. So the only data that you can use there are the times. So it's the times that have to be used. They have to make reference to those particular times. Okay. And because the time taken for the methanol to evaporate is the lowest, methanol must be the more easily evaporated. Here's the examiner's report on this. Most candidates identified that methanol was the alcohol that evaporates most easily and gained the first mark. The question asked for an explanation for this from the results, and as the results in the table with the values at times, the required explanation referred to the method taking the shortest time. Validity, anomaly, precision, accuracy, reliability are all terms that we will sometimes use in exam questions. The students are not expected to know the definitions of these and what is meant by them, but be able to appreciate where they crop up in questions and what their significance is. And the significance is listed in that particular booklet that's on the Pearson Edexcel qualifications website. Okay, it's under the resources section in the International GCSE section, and also in biology, chemistry, and human biology sections as well, because it's a guidance on using practical terminology in all four of the science subjects. Accuracy and precision are often mixed up with one another, as indeed two others that I've not listed on there, error and uncertainty. Here's accuracy. A student uses the apparatus to investigate the rate of reaction. During the reaction, the reading on the balances decreases because mass is lost. Explain how the cotton wool increases the accuracy of this investigation. And of course, what it does is it prevents acid spray from escaping, and that would have an effect on the loss of mass, which should, of course, be solely judged by the gas given off and escaping. Here's something on validity. You've got an experiment set up here in which you put different alcohols in and heat up with hot water. You put the alcohol on the evaporating basin, place it on top of the beaker, measure the time taken for the methanol to evaporate completely, and repeat with other alcohols. State two variables the student could control to make sure the results are valid. So we're not asking them to explain what is meant by valid, but we're asking them to understand what is meant by valid and therefore apply it to this situation. So obviously they need to use the same temperature of water, and they need to use the same volume of alcohol. Or more specifically, really, it should be the same surface area. But if they're using the same evaporating basin, it will be the same volume. Okay, right, so let's get down to doing some marking. We've got half an hour left to do some marking and then have a look at the support material. I may have to go through the marking a little bit quicker than normal. Have your pen and paper ready to write down the answers to these, because once again, of course, you may want to use these with your students, and you're quite at liberty to do so. Okay, there's the first one. You get ethanol from a dilute solution of caffeine and ethanol using that apparatus. Describe what happens to the ethanol in the apparatus, X. And the mark scheme has got a description that refers to two of the following points. Two of the following. There's only two there. M1, the ethanol cools, and M2, it condenses or forms a liquid. There you go. Simple. Right, so 1 mark for cooling and 1 mark for condensing or forming a liquid. So there we go, down. I don't think we need to spend much time on there. you can get your students to have a look at this one. They should spot that that's the cooling down, that's forming the liquid, so you get 2 marks. There's student 2. They got the 2nd mark for condensing. There's no mention of cooling, so no M1, 1 mark. Student 3. They got the condensers. No mention of cooling again, unfortunately, so only 1 mark. That was very, very common in answering this question. A lot of students didn't mention the cooling. They're just simply saying what happens to the ethanol. It condenses. Why does it condense? Because it cools. There were 2 marks. So why students expected to get 2 marks for simply saying it condenses, or it condenses and forms a liquid? I don't know why they expect to get 2 marks for that, because condensing and forming a liquid are the same thing. Interesting. Well worthwhile using these 2, student 2 and student 3 answers to emphasize 2 marks awarded. How are you going to get the 2 marks? What a perfect answer. I love that. I wish I could teach more of these students. Cools down 1 mark, condenses 1 mark. Note the consigned answer. That's all that's needed. So many students seem to think that because 4 lines were left to answer this question, they have to fill up all 4 lines. You can answer it on 1 line. Cools down and condenses. That's an excellent one to show your students. Keep your answer to as brief as possible, putting down all the information that's necessary. There you are, you got your marks. Okay, here's the next question. Okay, this is a slightly longer one to mark. Okay, part 1, the chromatography paper is placed in the solvent. Explain why the spots on the baseline are placed above the level of the solvent. This is a question that's been asked many times in the past. Explain which 2 felt tip pens contain the same dye. And the third one is, the student thought that both F and G contained only 1 dye. Explain why the student can be certain about one of the dyes, only one of the dyes. And there are 2 marks to each. Right, looking at part 1, why is the chromatography, the baseline, placed above the level of the solvent? So an explanation that's got, they will not dissolve into the solvent so that the dyes can then travel up the paper. Okay. Allow water for solvent. Part 2, E and H, and as the dye has got a spot at the same level, the same distance, same RF value, but you can only get M2 if you get the E and the H. M2 is dependent on M1. And the last one, an explanation that links the 2 points, that the student can only be certain about G as there's only 1 spot, and F is insoluble, so you can't tell. So just say F is insoluble or it's not moved, or words to that effect. That's what OWTTE means. But notice that you have to say they can only be certain about G because there's only 1 spot. That's important. Okay, so there's your first one. Look at part 1 first of all. Link it up to your mark scheme. Do not dissolve is M1. To move up the paper is M2, 2 marks. Right, have a look at part 2. E and H, M1. One of the spots is shared by both of them. Insufficient detail for M2. They have to say they've both got a spot at the same level. or travel the same distance, I've got the same RF value. So that's not good enough. Okay, so only 1 mark. Look at part 3. They can be certain about G as the baseline disappeared and only 1 spot formed high on the paper. Sorry about that. Hopefully my wife will answer that in a moment. Yes, she has. Good. Right, so as only 1 spot formed, and that's exactly what it says in the mark scheme. So they've got M1 for G because it only forms 1 spot, and the dies in F did not form spots on the paper, but remained on the baseline. They're insoluble. So that scores M2, so 2 marks. Okay, hope you're happy with that one. There's the next series. Have a look at part 1. So they do not dissolve as M1. No results will show is not sufficient information, so they only get 1 mark. E and H is correct, and have a look at the explanation. Times the same level scores M2, so 2 marks. Have a look at part 3. They can only be certain about G, but they haven't said that it contains 1 spot. So they've missed out some information. So they can't have M1. F did not move, scores M2, so they get 1 mark. Okay, hope you're happy about that one. Okay, there's the next one. They've crossed out dies and replaced it with inks. I don't want to penalise that. Allow inks for dies. So they get M1. And right at the very end, the inks won't move up, 2 marks. E and F is wrong. So the fact that they've written down that they've got one of the dies in both travel the same distance is not acceptable. No marks as M2 dependent on M1. In part 3, no mention of G, so there's no M1, but they've got he can be certain of F due to it not moving. Scores M2, 1 mark. Okay, and here's the last one, this particular question. Look at part 1 first of all. Don't dissolve, scores M1. The dyes don't dissolve into the solvent and rather go up the filter paper. Scores M2, 2 marks. E and H is correct. Both spots travel the same distance. M2, 2 marks. F is not separated due to it not moving due to its insolubility. Scores M2. G, on the other hand, moved, but displaying only one stain above, indicating one die. M1, 2 marks. Okay, hope you're happy with that one. I'll just leave it up for a little while longer in case you're making notes. Okay, next question. Calculate the RF value. This, of course, is where they need to take out their rule, measure the distances. So the first mark is for getting the distance from the baseline to the solvent being 65 millimeters or 6.5 centimeters. The distance from the baseline to the spot or die in millimeters is 39 or 3.9 centimeters. And then calculating the RF value by putting M2 over M1. Whatever their M2 and M1 is, they can have an error carried forward if they get those wrong, but do it the right way. In the notes column, accept any value between 38 and 41, because of course the spots are not just a single dot. So they may measure to different points on the spots. They may measure to the top, the middle, or the bottom. Okay, accept any value for M3 between 0.57 and 0.64. M3 is not awarded if the value is incorrectly rounded. Okay, right, so here we go. There's the first one. Well, straight away you can see the 0.6, so it must be all 3 marks awarded. Okay, and the only thing is here they've done it in centimeters rather than millimeters, and that's perfectly acceptable. So there's your 3 marks. Nice simple one. Okay, next one. M1 for 6.5. M2 for 4, because it says you can accept any value between 38 and 41. So that means 3.8 and 4.1 is acceptable. But of course, they've divided them the wrong way around. They should have had 4 over 6.5. So that's wrong. So only 2 marks. Next one. M2 for 4. 2.5 is wrong. And they've multiplied instead of divided. So that's wrong. 1 mark. Student 4. M1 for 6.5. M2 for 4. That's wrong. Incorrect evaluation. 4 divided by 6.5 should be 0.62. So they score 2 marks. Okay, doing practical work. As I've already mentioned, there are 12 core practicals that form part of the subject content. Exam questions expect students to be familiar with methods for these practicals. Questions also expect students to apply their knowledge of practical methodology to unfamiliar scenarios. I'm going over old work, but I'm just re-emphasizing. So why should the student do practical work? So some questions for you to consider after you leave this presentation. Are the students getting the knowledge or skills from the practical activities that you set them? Well, from the core practicals they should do, providing, of course, you quiz them about why they're doing them as well as what they're doing. When do you do practical activities? Before or after teaching the theory of a topic? Is it worthwhile sometimes doing a practical to introduce the theory? I think the answer is probably yes. And here's some examples of some practicals that I used to do with mine. Teaching approaches, fact or investigative. Why does copper turn black when heated in air or a Bunsen burner? Well, you could just simply tell them copper reacts with oxygen to form copper 2 oxide. Fact. What have they learnt? Okay, a fact. They've learnt a fact. Good. All right, investigative. What may have caused the black substance to appear? They may turn around and tell you the Bunsen flame or the air, because the copper's been in contact with both. How can we find out which? Your students may answer, heat the copper in a vacuum. And you say, well, how am I going to light my Bunsen burner if there's no oxygen? So it's not practical. Or heat the copper in a test tube so it's not in contact with the Bunsen flame. Ah, good, right. So you give them all a test tube, give them a piece of copper, send them away and get them to heat the copper. And you find, of course, the copper still goes black. So it must be something in the air. Can't be something in the flame. How can we find out which gas in the air is responsible? Answer, heat the copper in each gas separately. Again, not practical, unless you happen to have cylinders of oxygen, nitrogen, carbon dioxide, and argon available. And I doubt many schools have got that. Right? So it's not really practical. But however, you could heat the copper in a sample of air and find out the percentage of gas used up. This is the old classic experiment of taking 2 gas syringes and having a thin silicate tube with very fine copper turn-ins in it, and starting off with 100 cubic centimeters of air in one gas syringe and no cubic centimeters of air in the other, and pass the air over the copper until the volume stops decreasing. And hopefully you can see that 20 cubic centimeters will be used up. So the copper is combined with oxygen. Look at all the investigative techniques involved there, the skills they've learnt, the way in which the thought processes have developed. They've learnt a hell of a lot more of why copper turns black, and it will prepare them for answering AO3 questions. Just a thought, is something you might want to consider doing with them. Another experiment I used to do before I taught practical on rates of reaction. Good, I'm glad it's gone wrong. I'm a great believer in giving them experiments in which the results turn out to be that they get are often the ones that they don't expect to get, because then they've got to work out why and what they can do to make it a valid test. And what I got them to do was to put 1 cubic centimeter depth of 1 mole per dm cubed hydrochloric acid into each of 3 boiling tubes, leave 1 tube at room temperature, put one in a water bath with a large beaker at 40 degrees, so around about 40 degrees. Doesn't have to be exact, round about will do. Place the third in the water bath at around about 60, and then tell them that they're going to add 1 cubic centimeter, 1 centimeter strip of clean magnesium ribbon to each tube, and measure how long it takes for the magnesium ribbon to completely disappear. But before they do it, predict the order of disappearance and then do the experiment. I got them to write up their order that they expected. Okay, then get them to do it. The prediction, of course, is that magnesium will disappear first at 60 and last at room temperature. Outcome, the magnesium very often, and in fact usually in my experience, disappears first at room temperature and last at 60. And you get cries from them, my experiment's gone wrong, can I do it again? No, it hasn't gone wrong, you've got your results, write them on the board, come on. But they're wrong, put them on the board, all right, write what you've got. Okay, and in most cases, that will be this case. And then you say to them, well, why is not that not matching your prediction. And they'll say, well, it's because it's gone wrong. Yeah, but why has it gone wrong, in inverted commas? And eventually you can get out of them that the reason is that gas is given off so violently at 60 degrees C, the magnesium continuously lifts off, the acid fall backs down. A little bit less so at 40, but at room temperature it sinks. And there you go. Okay, interesting. And then you can start work on rates of reaction after doing the experiment. Just a thought for you. Okay, on the Pearson Qualifications website under resources, you can find a core practical guide, which is I encourage you very much to find. It's in the teaching and learning materials section on the International Chemistry GCSE website. Okay, so I advise you to download that and have a good read through. You'll find some very, very useful information about the core practicals for chemistry there. Okay, right, now I'm not expecting you to read all of this material on the next few slides, but you have got in your download a PDF version and you can sit down and read all of this at your leisure. You know, I've been referring to this particular page on the Pearson Qualification website. This is the International GCSE Chemistry Linear Specification for Chemistry 2017, okay? And you can see that teacher and support training, you've got course materials is the important one. You've got the specification and sample assessment materials. You've got the exam materials. So the little green one, second one down on the right-hand side. Okay. And you've got teaching and learning materials there. Go to that section and have a look and see what's in each of them. You'll find some very, very useful information in all of that lot. Okay. Teaching and learning materials in particular, there's a quick breakdown. Again, don't try and assimilate all this information now, all right? But you can see past papers, you've got examiners' reports, mark schemes, and the question papers. You notice the ones that have been selected out have got a little padlock next to them. They can only be accessed if you have a username and a password, and you can get the username and passwords from your exams officer. The reason they're padlocked is to stop students accessing them. So don't give the username and password to students, because then you won't be able to use those papers for mock exams. And then in the teaching and learning materials, you've got a lot of guidance, you've got course planners, exemplar material, you've got scheme of work I mentioned earlier, you've got the topic support, which I'm going to come on to in just a moment, okay? And then you've got past training content over there as well. The guides, you've got the Maths for Scientists guide, which I very strongly recommend you to have a good look at. It outlines the content that students will have covered in their maths lessons throughout Key Stage 3 and Key Stage 4. So you can use it to help you understand the different areas of approach in maths and therefore support your teaching of the mathematical content in science lessons. Do it the same way that the maths department do, so that the students are not conflicted with different methods of doing things. Try to fit in with the maths department. And if necessary, go and talk to the maths department, which I have done in the past, about how they approach particular topics. Okay. Another guide is the core practical guide. Again, it's got an introduction to each of the 12 core practical activities, a description of the practical with some useful hints and tips, and some questions to use with students to test their understanding as to why they do the experiments in the laboratory. It's got a past paper question where relevant to use as a homework activity. This is one that I wrote specifically for this specification on chemical equilibrium, and it all started back in 1984 when I read an article in Education and Chemistry by Alsop and George. The article was entitled Le Chatelier, a redundant principle, in which they argued that the use of the principle was counterproductive to the understanding of chemical equilibrium, a view which I share wholeheartedly. And there's so much research been done since 1984 to date that supports that, which is why I personally would never use Lusitani's principle in my teaching of qualitative um, discussions on how the effect of changing the variables affect positions of equilibrium. Okay, have a read of it and see what you think. You may think, no, I don't like that. It's not for me. Okay, you may agree with me. I'm not trying to force you into a particular way of thinking. I'm just supplying you with suggestions is for something you might want to think about. And remember that it's not required for international GCSE chemistry, and a number of students often refer to it in their answers. They won't get any marks, so why bother? Okay, there's the chemical bonding guide, which is another guide that I wrote specifically for this qualification to support the teaching of chemical bonding. Okay, um, a lot of teaching around chemical bonding revolves around the use of the octet rule, which I'm very much against. The chemical bonding and related ideas about chemical stability stroke reactivity is acknowledged as being tricky to teach, and with very good reason. Okay, research has shown that students commonly acquire misconceptions about chemical bonding. Some of these can be persistent and may present significant barriers to students' progression and understanding of more complex ideas. Many students studying at GCSE level and also some studying at both A level and beyond appear to develop a firm belief that species with full outer shells are outer shell octet configurations are energetically more stable than species with other electronic configurations. This is very far from the truth. The electronic configuration of 2,8 for an argon of neon is not more stable or less stable than the electron configuration of 2,8,1 for sodium atom. They're both stable. The only reason why sodium atom can lose an electron is if you put it into a situation where it is energetically favorable for it to do so. It doesn't lose it on its own. It's not unstable. It keeps its electronic configuration of 2,8,1. It's a stable electron configuration. Okay. Anyway, have a read of that. It gives you a way of teaching chemical bonding without mentioning the octet rule, which you may or may not, at the end of the day, agree with. Okay. I remember when I was invited by the Institute of Education in Malta to go over and give presentations on misconceptions and myths and misconceptions in teaching GCSE and A-level chemistry. I taught the A-level students, A-level teachers one day, and before I could teach the GCSE teachers the next day, the A-level teacher said to me, could you please ask the GCSE teachers not to use the octet rule when you see them tomorrow? And I said, it's okay, it's on the agenda. Right, results plus. This is something again for you to read and analyse and get access to via your exams officer. Incredibly useful because it gives you analysis of your students and their own teaching performance, and it can give you in-depth data on the performance of a candidate or a whole class or a school in reference to the cohort. You can use it to see which questions and spec points students have performed well and poorly and use these in their choices around revision. Okay, so Results Plus is another tool for you. Exam Wizard is another one. You've got all the past paper questions on there and you can access them by papers, you can access them by topics, and you can access them by assessment objectives. So you can create test papers of questions in AO1 questions, AO2 questions, or AO3 questions. Again, once you access Exam Wizard, there's an online guide there which you can read to find out how to use Exam Wizard. Okay, it would take me, we could go through it, but it would take a good half an hour to 3/4 of an hour to go through how to use all the things. You're better off accessing it and learning it from the online guide. Okay, you've also got access to scripts, which is a free online service that you get from Results Day onwards, where you can access your student scripts and see exactly how it's been marked and how the marks have been awarded. Okay. Um, and that can help you to decide uh, whether or not to ask for a remark on a particular script. If a student comes to you and says, I think I did better than the mark I got, you can access it, look at it, see how it's marked, and say, no, actually, it's been marked correctly. So I don't think it's worth your while putting in the remark. Or you can say, yes, I think I can get another 5 or 6 marks. It might be worth putting in a remark. It's up to you. Okay. There are, of course, published resources. There's that book. A reminder, you do not have to use Pearson published resources to support the teaching of this qualification. You can use any resources, any textbook, any resources from any publishers or anything online. It doesn't have to be Pearson resources, okay? But there is a Pearson book available should you want to use it. There's also the Teaching Hub, which is a paid for resource. It's excellent because it's got lots of information in it, exam preparation resources, continual professional development support. Okay, whether you're a specialist or a non-specialist teacher, you've got a lot of information there, but it is a paid for resource, and obviously that would have to come out of your budget. There's also the subject teacher and advisor support, and their details are on the website, but you've also got them on the PDF version of the pack, so you can contact them for any help and support that you want, and they will sort it out for you. Anything to do with the qualification, anything to do with the marking, the answers in the mark schemes, the how do I go about this particular bit of administration, they will help you and sort you out, okay? You've got the Pearson Professional Development Agency, okay, which you can sign up for, and you've got the URL down at the bottom there, and you can see that on the PDF version, okay? So have a good read through that and decide whether or not that's worth your while signing up for. You can also sign up for the newsletters, so you can scan the QR code or fill out the form. Okay. Right. So very quickly, are there any more questions? I've gone slightly over the time, but we don't get penalised these days for doing so because it's a Zoom. So any questions that are outstanding at the moment? No, there's nothing coming to the chat box. So all I can say is thank you. I hope you found this useful. Okay. I've tried to give you as much of my experience, pass on my experience as possible to give you some suggestions as to how to go about delivering the teaching to support your students in this qualification. So there we are. Thank you very much indeed for your time, and happy teaching. And if you are attending the International A-Level equivalent session on Thursday, I will see you there as well. Thank you.